Good afternoon, dear student, and welcome to this other edition of our numerical method class. Today we are going to tackle the concept of Fourier series and trigonometric polynomial. In approximation theory, if you recall, the purpose is to approximate a function using various methods. But it turns out that there are functions that need to be approximated by sine and cosine, particularly when it comes to periodic function. If you have a periodic function, you cannot use a polynomial to try to approximate a periodic function. We know all the drawbacks of interpolating polynomial. So in order to approximate a periodic function, it is required that you also use periodic functions. And the basic periodic function that we know are sine and cosine. And sine and cosine form the basis for periodic functions. So back to the history of Fourier series. Actually, the name is coined after Joseph Fourier. The name is in his honor, because he contributed a lot into the study of trigonometric series. But before Fourier, there are some scholars who investigated the matter of approximating periodic function. We have people like Euler, D'Alembert, and Bernoulli. Particularly Daniel Bernoulli, because you have Joseph, but that was Daniel Bernoulli. So the main motivation behind the work from Fourier was the solution of the heat equation. Heat equation is a partial differential equation that modeled the flow of heat in a metallic rod. So that's what he was solving. So he's the first person who expressed the solution of the heat function, of the heat equation, using the superposition principle. Before him, those who solved the heat equation just used a particular initial condition, a simple initial condition. Let's say, for instance, the source term. When the source term is a sine or cosine function, the solution can easily be obtained. But Fourier came with the idea that you have an arbitrary source term, right, which is a periodic function, and that's how he came about with the solution. So how was his solution? I will try to write it on the slide. This is how Fourier's solution to the heat equation was written. So he wrote the following. So he wrote a solution, phi of y equal to a0 cosine pi y by 2 plus a1 cosine 3 into pi y by 2 plus a2 cosine 5 pi y by 2 plus. So you can see already that this is a series in terms of cosine. So this is we can rewrite this as a sum AK like this, and cosine 2k plus 1 pi y by 2. This is a function of y. In that case, yeah. Now k runs from 0. If I substitute 0 there, you can see that this will be cosine pi y. Then when k is equal to 1, you have 3 into pi y by 2. So that is how he expressed the solution. So that was the fundamental idea, and other people came later on and improved the method. Okay, so once we have set the stage, let us define what is Fourier series. So by definition, we first need to define what is a periodic function. So given a function f, function is periodic and with period pi if and only if for any x, f of x plus p is equal to f of p. So p here is the period of a function f. It means that the function will repeat itself after p units, the period. But in our study, we'll assume that the period is 2 pi. So we stick to that. Why? Because even if the period is not 2 pi, we can use a change of variable to make it 2 pi. So, definition. If a function f is periodic with period 2 pi, we also assume that the function is piecewise continuous on the interval negative pi pi. The Fourier series denoted by f, s sub f, that would be a better notation, f sub f, for f if, is the definition, the function is, s sub f of x is equal to a0 by 2 plus the infinite sum, k running from 1 to infinity, of ak cosine kx plus bk sine kx. Here you can see that they are coefficient ak and bk, and they are determined, or they are defined via what is called Euler's formula. So ak is equal to 1 by pi integral from negative pi to pi f of x into cosine kx dx for k running from 0 to infinity. And bk is equal to 1 by pi into the integral from negative pi to pi f of x sine kx dx. This time k runs from 1, 2, 3 up to infinity. So the remark here is that for b, b0 does not exist. The only sub-zero that exists is for a. And you can see that in this formula, we have written a single formula for both the case where a is the subscript is 0 and non-zero. But in other textbook, you will see that here, this constant term, isolated constant term, is written to be a0. And for that, you will be given, the formula will be different from the one given in equation 141. So we will stick to this definition. Okay, so in order to derive this Euler's formula, ak and bk, we use the property, the orthogonality properties of sine and cosine function, which are given by these 5 formulas. We will skip that for now and dive straight into a theorem. We need a theorem. In the definition, you can see that equation 1.40 is just a definition. So we don't have any convergence result on the series. So this is just a definition because the definition can be infinity, right? S sub f of x can be infinity, but we need to state a theorem that gives us a convergence result. And if this series converges, it will converge towards either f of x on point where x is the function f is continuous, and it will be the jump, the average of the jump discontinuity at any point of discontinuity. So let's look at the theorem. We assume that the Fourier series of f is given by s sub f of x for any x over the interval negative pi pi. Now we have a condition here. If the first derivative of the function f is piecewise continuous. We know that f itself, by definition, by construction, by the hypothesis here, that f is piecewise continuous. We also impose that the derivative is piecewise continuous and has a left hand and right hand derivative at each point of this interval. So if these two conditions or these two requirements are met, then the Fourier series f sub f of x is convergent for all x in the interval negative pi pi. And s of x will coincide with f of x. So that is, the Fourier series f of x will converge towards f of x at each point of the interval negative pi pi. Obviously, this is true for points where f is continuous. But because f is a piecewise continuous function, there might be points of discontinuity. And at those points of discontinuity, the series will converge towards the average of the left hand and the right hand limits. Given by f a minus and f of a plus, respectively. Okay, so let's look at the particular example. Let's compute the Fourier series of this function f of x equal to x by 2 for x in the interval negative pi pi, and the function is extended periodically over the real line by the equation f of x plus 2 pi equal to f of x. That is the periodicity of the function. So we want to show that the Fourier expansion is given by this formula, and that's what we are going to do. So we are going to compute AK and BK for this function, this periodic function. So I will open a new slide, and we are going to compute those coefficients step by step. But the first thing before proceeding, if you look at the expression of this function, okay, that's a result that we'll use later on. So let me keep it. I wanted to skip a step. So let us compute AK and BK. So our function f of x is given to be x by 2 for x in the interval negative pi pi, and we are told that the function is extended periodically. Okay, so if we write the coefficient, first of all, let me write the general expression of our Fourier series of the function f. So it is equal to a0 by 2 plus the sum over k running from 1 to infinity of ak cosine kx plus bk into sine kx. So ak is equal to 1 by pi, the integral from negative pi to pi of the function f of x into cosine kx dx. So there are two steps. This formula holds for k running from 0, 1, 2 to infinity. So we have to compute separately the case when k is 0 and the case when k is non-zero. Why? Because when k is non-zero, we have the cosine present. When k is when k is non-zero, cosine will be present. When k is 0, we will just integrate the function f of x without a cosine. So we have to distinguish the two cases. So let's assume that k is 0. So if k is 0, our a0 is equal to 1 by pi integral from negative pi to pi f of x dx, which is nothing else than the integral from negative pi to pi x by 2 dx. And this is 0. Why? Because this function is an odd function integrated over an interval centered at 0. I mean, we can see that the interval has the same distance from the left to the right of 0. So, yeah. So it will give us 0, but we can substitute. This will give us 1 by pi x squared by 2 from negative pi to pi. So you can see that when we square the value at pi and the negative pi, it will be the same. So when we take the difference, it gives us 0. Now, when k is non-zero, our ak is equal to 1 by pi into the integral from negative pi to pi f of, okay, I can substitute that directly, x by 2 cosine kx dx. And I don't need to keep it 1/2, I can factor. So this gives us 1 by 2 pi integral from negative pi to pi x cosine kx dx. So we can use integration by part. Denote this by u and all this by dv. So if we set that, this integral will be equal to, I factor the 1 by 2 pi. Now inside the integral, I will write inside the square brackets, I will expand this integral. So u dv, so this is the integral from negative pi to pi u dv, which is equal to 1 by 2 pi uv from negative pi to pi minus the integral from negative pi to pi v du. Right. So we can compute this directly. We know already the value of u. U is x. So this is 1 by 2 pi factor. Okay, so u is x. V, which is the antiderivative of cosine kx dx, it is sine kx by k, and we put the limit evaluated these two limits. Okay, so those are the limits of this evaluation. So this is u, this is v, minus the integral from negative pi to pi v. So we know already that this is v du. So if we compute the differential of x, it will be dx. So this will be sine kx by k dx. Then I close the curly bracket. Now this integral, in order for me to compute that integral, I need to use the trigonometric circle to see exactly what is going on here. If I compute the trigonometric circle, okay, what is happening here is the following. As we all know, this represents cosine. This represents cosine of the angle, and this represents sine of a given angle. If I take an angle here, theta. Now, I will evaluate this at pi and negative pi. So let us write that. So this will be equal one by 2 pi integral. Now I evaluate this function at those 2 points. So here we have x. Sorry, x is equal to pi. So this is pi sine k pi by k. K is non-zero. Minus at negative pi, so it will be plus with the negative. We have another pi here. Sine of negative pi. So this negative pi, I can take it out because sine is an odd function. By k, and there will be negative here. So already this will cancel out. And even if it did not cancel out, oh sorry, I think there's a k missing here. So this is k pi. Okay, minus the integral from negative pi to pi sine k x into by k. So even if this did not cancel out, because you can see that we subtract the same term, it will cancel out. But even if this were, let's say for instance, positive, each time you see sine k pi, it will always be 0. Why? Let's look at this. K pi, so this is our trigonometric circle, the positive direction. This angle is 0. This is pi by 2, or 90 degree. This is pi. This is 3 pi by 2. And this is 2 pi. So when I start from here, it is 2 pi. After a complete rotation, it becomes 2 pi. Okay, now if I'm computing sine of k pi, where k is an element, is a, let's say, an integer, right? So when k is equal to 1, we have sine of pi. So we will be here at this point. And at that point, to read the sine, I project it on the y-axis, because to read sine, I project on the y-axis, it will go to 0. Now, when k is 2, I will be here. Similarly, I'm on the x-axis, so if I project on the y-axis, the value will be 0. When k is 3, I will be here. So you see that k pi will be oscillating between these two positions, the position of pi and the position of 2 pi. Each time I rotate, by pi from a given position, let's say if I'm at the position of 0 or 2 pi, I rotate by pi, I find myself here. If I rotate by pi again, I find myself there, by pi, by pi, by pi, by pi, by pi, by pi, and each time. That is it. Now, if I'm here, the value, because the radius here is 1 for the trigonometric circle, the radius is 1. So if I measure here, this will be negative 1. That is in terms of the value, not the angle. The value will be negative 1. But if I'm here, the measure of the radius here is 1. So the value here is 1. So sine k theta will always be 0, right? Because I will be projecting there. So the value will be 0. I will be here. If I'm here, it will be 0. So anytime this will always cancel out, regardless of whether this subtract and give 0 or not, this will always be 0. So that is a good remark I wanted to stress on. So we can proceed with this integral. So the final result at this stage will be negative 1 by 2 pi integral from negative pi to pi sine kx by k dx. Okay, I can factor by k or I can leave it, doesn't matter. Now, here I can integrate directly because this is the identity, I mean the antiderivative of this expression is obvious to compute. So, for this one, the antiderivative, we know that the antiderivative of sine is negative cosine. So this will be positive with a negative cosine. So this will be cosine k pi, kx and by k square. Because you see, if you differentiate that, k will multiply the sine and k square will cancel out, and then you get k. Right? With the negative will become positive. Now you evaluate this from what? From negative pi to pi. So in other words, this will give us 1 by 2 k square pi or 2 pi k square, it doesn't matter, the order does not matter. And in the bracket of parentheses, the expression here, we will get cosine of k pi, cosine k pi minus cosine negative k pi. And because this is the cosine function is an even function, is the same as this. You can put a plus there. Now you can see that we have cosine k pi minus cosine k pi. This will cancel out and give us 0. But I want to use this opportunity to give the general formula for cosine k pi, because it will appear a lot of time in the integration or in the computation of the coefficient of Fourier series. So similarly to what I mentioned here for the sine, now for cosine, you can see that cosine, if I want to read cosine of k pi, we know already that k pi will oscillate between these two positions. But now if I'm reading the cosine, because this is already on the x-axis, and that is where we read the value of cosine. It's already there, so we don't need to project because it's already on the axis. So if I am on this side, if my k is on, allows me to be on this side, which means that k is an odd value, that is pi, 3 pi, 5 pi, 7 pi, and so forth, I will be here. Then the cosine of k pi will be -1. But if I land here, that is if k is even, like k is 0, k is 2, 4, 6, 8, 10, and so forth, the value will be 1. The value of the cosine of that angle will be 1. So we can sum all that information into the formula cosine of k pi is equal to 1 if k is odd, even, when, here, even, and -1 if k is odd. So this is something that you should bear in mind, and it's easy to remember using the trigonometric circle. So we conclude at this stage that ak will always be 0. We computed a0 and ak when k is different from 0. They all give us 0. Right. And that is exactly what we have in the slide. Okay, so we expanded, I see we expanded it a bit differently. We use 1 by 2. We have two expressions, the sign. Okay, we first, we cancel out the sign, we did that, and we also cancel out the cosine. So here is group in one go. But what we did that in stages. So let us do the same thing. Let us perform the same computation for bk. So for bk, we can write the formula bk is equal to 1 by pi into the integral from -pi to pi f of x sine kx. So we don't need to distinguish the cases here because we know that k for b, k. We always start from 1, 2 and continue, so we don't need to distinguish the two cases. So if I substitute, we get this expression, x by 2 sine kx dx. Of course, I can take that the 2 out to make our computation simpler. So we proceed in a way similar to the previous. So I would just so we can do the same thing. This we call this u, and all this expression is dv. I have the choice between computing the derivative, everything here on one side, so let's do that. It will not be obvious for everybody. So if I draw a line here like this, if my u is x and dv it's sine kx, here we can compute du is dx, and v, the antiderivative of that, is negative cosine kx by k. And it's easy to check. If you differentiate this, the derivative of cosine is always negative. With the negative in front, become positive, and then sine times k, which is the derivative of this. If we differentiate this, because this is a chain rule, if you differentiate this, you have a factor of k. That k will cancel out with the k in the denominator. You get sine kx. It is always good to check. Make sure that you get the correct formula than to rush and realize later on that your computations are wrong. Okay, so now if we expand that formula, we have 1 by 2 pi into uv, so we know that our uv will be negative x cosine kx by k, that is our uv, of course evaluated at negative pi and pi, now minus the integral from negative pi to pi v du. Now what is v? V is negative. With this negative I can put positive there, and du is this one, so I will take this. So this will be cosine kx by k into dx. So if we evaluate this, okay, let's keep it for now. Now antiderivative of the other term, 1 by 2 pi here, so we can keep this negative x cosine kx by k. Now if we compute the antiderivative of this, this will be sine kx, the antiderivative of the denominator, by k. With this k again, you get k squared, and that is evaluated at this point. So this is what we finally obtain, and we know already, we already explained that sine k k pi will always be 0 because that will fall on the x-axis. So if you project on the y-axis, you always get 0. So what we are left with is to evaluate these 2 points. So this gives us 1 by 2 pi. We evaluate, so we write this at, we evaluate this function at pi, so that will be negative pi cosine k pi. Obviously, since k is a common denominator, I can factor that k. And minus the same expression. So I have minus here. Now with this it's fine. I keep the minus. Now if I write this minus minus, it will be pi cosine negative k pi. But we know that the cosine function. Okay, let's write that negative k pi. Now we can rearrange this as 1 by 2 pi k into, so this expression if I expand this, it will be exactly the same as this one. So it will be negative 2 pi cosine k pi. Because we have exactly the same expression that will repeat if I remove the bracket, and this is absorbed by the cosine. Okay, so this is what we have. So we can also easily see that we have a factor of 2 and pi, a factor of 2 and pi. So finally the result will be one by k. Actually, we have a negative here in front, so it is negative 1 by k cosine k pi. And if you recall what I said in the previous slide, this is negative 1 to the k, to k. So this is negative 1 to k, to the power of k. But this negative in front also is negative 1. So if I multiply negative 1 to the 1, because negative can be written as negative 1 to the 1. So if I multiply negative 1 to the 1 with negative 1 to the k, it gives negative 1 to the k plus 1. So this gives us negative 1 to the k plus 1 by k. So that is the expression of our bk. So we can write finally that bk is equal to negative 1 to k plus 1 by k. Now substituting back into the expression of our Fourier series, so our Fourier series will be equal to what? A 0 is 0, so all that part will cancel out. So now k will run from 1 to infinity. Bk sine, so bk will be negative 1 to k plus 1 by k sine kx. Now we can exhibit a few terms. So when k is equal to 1, if I substitute 1 here, it is positive, and then we have sine x by 1, because k is 1. Now when k is 2 plus 1, it will be 3, so there will be a negative here, and then we have sine 2x by 2 plus sine 3x by 3 plus, minus sine 4x by 4 and so forth. So this is what we obtain. And which is exactly what we're asked to prove. So we can see sine negative 2. So we start k equal to 1, k equal to 2, k equal to 3, k equal to 4, and so forth. And the sign is alternating, positive, negative, positive, and so forth. All right, so we will stop here for today, and we will continue next time. I hope you have enjoyed this video. Thank you for your kind attention. God bless you, and see you in the second part of this video. Bye.